Okay, so this is another one of those Bernoulli ones, yeah? So first let's divide here by xy squared. So we will get, uh, so divide everything by xy squared. So we will get y prime equals y over x um, plus so this is y over x, and then the x squared will be if we divide by xy squared, we will get x y to the minus 2. Okay, and what we're going to do is we're going to move this to the right to put it in the standard form. So y prime minus 1 over xy equals xy to the negative 2. And this here is our n. And since we have that n there, we will use Bernoulli transformation to reduce it. Okay? So then we will say let v equals y to the 1 minus n. So that means v equals y to the 1 minus 2, because n is 2, so that's y cubed. So y is v to the 1/3. Okay? And so y prime, so now we will make the transformation from u to v. That's v. So we will say dy over dx is equal to dy over dv times dv over dx. And dy over dv is just the derivative of this. So this is 1/3. 1/3. Wait, let's make sure this is, so this is over xy squared, so this is x y to the minus 2, and this is 1 over x y. Okay, good. So this is 1/3 v to the minus 2/3 times dv over dx. Okay? And so we will substitute into the differential equation. We will substitute into this one right here. So we will get y prime, which is, so let's call this equation A. So A becomes y prime, which is 1/3 v to the minus 2/3 times dv over dx minus 1 over x. Y is just v to the 1/3. Yeah? And equals x y to the minus 2. So that's v to the minus 2 over 3. You have a question on that one? And now we will multiply this whole equation by 3v to the 2/3, so we can make the first term a 1. Yeah, go ahead, ask.
I got v to equal this, so why would be this cube? It's strange thing.
No, you got v secant cube x equals the integral of that.
Yeah, so
The integral of that is just tan, because
Yeah.
1 secant, yeah.
yeah, I did this.
So that means v, you just divide by secant cube
Yeah, I
x.
did that.
Yeah, and then y is just, yeah.
Alright, so y is just this cube.
No, y is that raised to the minus 1/3. Because y is v to the minus 1/3. Look back in your equations.
The same thing. One over.
No, minus 1/3. Minus
Oh,
1/3.
wait, yeah.
So then, continuing on this one here, we get dv over dx minus 3 over x, since we're multiplying by 3, and v to the 2/3 and v to the 1/3 is just v. And this here becomes x times v to the 0, which is 1. And so now, from here, we will use the integrating factor method to solve this. So what we're going to do is we're going to multiply here by mu, here by mu, and here by mu. And we're going to claim that d over dx of mu v, you have a question? Equals mu times x. And
How
when,
did you get the
and when we FOIL this, yeah,
y? You said you got wasn't v y to the -3?
mu over dx by the product rule has to equal mu of x. And we will compare these two equations. These two are the same. These two are the same. So 1 second here, Ben. So that means those have to be the same. So that makes d mu over dx equals minus mu 3 over x. Okay, go ahead, Ben. What's the question?
Wasn't v equal to y to the -3?
V equals y to the -3, yeah.
Yeah. So
You're finding y.
Yeah, I know. So well, I got v. So then y would be so y would be v to the 3.
No, v is y to the -3.
Yeah.
Yeah, so you have to flip it.
Right.
Okay, so back to here. So that means we can separate the variables here, and this becomes d mu over mu equals minus 3 dx over x. And we could just integrate both sides here, and we get ln u is equal to, oops, here is just an x. So equals ln x, and then we can raise this to the -3, which tells us that mu has to equal x to the -3. So this is our integrating factor, and we're gonna go back to our equation right here. Let's call this equation here b, and we're gonna plug in the integrating factor there. So b becomes d over dx of x to the -3 times v um, Oh yeah, we forgot the 3 here. There's a 3 here. That's what I was thinking. So there is a 3 here. Wait. Yeah, 3x. So this becomes uh, and there's a 3 here. Let's see, does this get us the product rule? Wait, so we've got 3 minus 3 over x 3, and here we've got x times 3. Okay. Wait, something went wrong here. Let me erase this. I'm gonna erase this. Okay. So now this is 3x. And then if we differentiate that, we get mu dv over dx plus v times dmu over dx equals 3x times mu. So that just means dmu over dx has to equal minus 3 over x mu. Yeah? Separate the variables. So you get d mu over mu equals minus 3 dx over x. And we're going to integrate here and integrate here. And then we get ln mu has to equal to ln x raised to the minus 3. So yeah, mu is equal to x to the minus 3. Okay, so we're going to plug this into equation B. So equation B becomes mu v Okay, equals 3 mu x bx to the minus 2. Okay. So we're gonna now take this dx, put it here, and integrate both sides. So we will get x to the minus 3v. You have a question? Oh, on this one, did you get the right answer on the other one?
Yeah, I didn't.
Yeah, it's fine. It's fine. That answer is correct. On this one, what you have to do, you have to divide first to isolate the y prime. So divide the whole equation by xy squared. Yeah, so you can put it in the standard form. So then from here we can get our v to be minus 3 x squared. Okay, and now we know that v is v is y cubed. So y is, oh, plus c, we forgot the c here. Not good. So let's delete this. Let's open this a little bit more. So then we're going to get plus c over x to the minus 3, or we can just say x cubed, either way. Okay? So we know now that y is just v to the 1/3. So we just need to raise this to the 1/3. So we get y equals minus 3 x squared plus cx cubed raised to the 1/3. This does it using Bernoulli's transformation to reduce the differential equation. We find v first and then y. You have a question?
Here we have a y to the negative 2.
Mm-hmm.
So then we would add 2 to it, or we add, we'd add 3 to it. Add 3 to the x bar.
Y.
Y to both. So get it to y to
Yeah, but first move the term that has the y in here. You understand what I'm saying? You need to put it in the standard form, which is this form right here. So you move the y term to the left, and your n is to the negative 2.
Oh, yeah. Oh,